Hello and welcome to my video for the Lab 4. So in this experiment we are analyzing the movement of a weight oscillating on a spring using tracker, and then we're creating a computational model simulating that exact same motion, and we're comparing those models and noting specific changes in energies as the experiment occurs, basically trying to dictate and conclude whether or not the energy principle is satisfied. And then for an overview of the main results, the energy principle was concluded to have been satisfied in the oscillation of a mass on a spring. Some of the fundamental concepts used in this experiment were Newton's second law, which basically dictates that the sum of all forces on an object is equal to the change in momentum with respect to time. Another concept that was used in this experiment was the energy principle, which says that the change in individual energies on the experiment, or the sum of those, is equal to the work done by each individual force, in addition to the change in internal energy of the object. And so the specific energies that were used in this experiment were kinetic energy, gravitational potential energy, and potential energy of a spring. So in the experiment, the system was defined to have been the mass, spring, and earth. And the surroundings was everything that wasn't those three things, basically. So let's say the attachment point for the spring, or the wall, anything that isn't the spring, mass, or the earth. Initially, the spring was started at rest and held at a known position, and the video was started and the mass was released. The oscillation was recorded in a video, which was then transferred to tracker, and the position of the mass was analyzed. A computational model was created using the concrete data, and then the models were compared and further conclusions were made. So to get into a bit more, the tracker analysis of the video led us to extract these specific values. So the mass of the weight, the spring constant of the spring, as well as the stretched and relaxed lengths of the spring as well. You can see the position data plotted against time over here. You can also see it on this little table. The data for the X and Y positions were then put into a computational model and compared with the motion of the object were it to occur in an ideal situation. So you can see right here, the motion of the object, and the blue line would be its motion in an ideal circumstance. And so up here, we calculated each of the individual energies, and then we calculated the net force on the object, and then with each of the forces, we said the net force is equal to the sum of the gravitational and the spring force acting upon the mass. And then in order to properly simulate the motion, we needed to use the position update formula as well as the velocity update formula, and then these both allowed us to calculate the changes in specific energies, which we defined over here to be the final energy minus the initial energy for each time step, which we defined to be 1/210 of a second. And so the comparison, you can see that the motion of the mass on both the X and Y axis are both plotted against time down here. You can see a bit of a discrepancy between the red line, which is the tracker model, as well as the blue line, which models the movement of the mass. And which leads us into our error discussion, and basically some random error that could have occurred in the experiment was selecting points in the tracker model. So each of the data points were hand selected, so it's possible that they weren't exactly accurate to the true position of the mass, which may cause small fluctuations like we saw in the comparison. Some systematic error, which could have accounted for that big shift in the tracker model versus the computational model, would be the unaccounted for drag force. The computational model didn't account for the drag force opposing the object's gravitational force, which we saw modeled in the tracker model. And so this force was constantly affecting the mass, and so likely contributed to the discrepancy between the model and the experimental data. And so what does it mean? Satisfying the energy principle. Because we're assuming the system is isolated, we are assuming each of the individual forces in the net force are doing no work upon the system, and so we have to assume that the change in energy equals 0, which is supported by our computational model. You can see that the energy remains 0 throughout the experiment. And then what does it mean for oscillation periods? So a period is the time taken for the system to complete one full oscillation. You can see this as the time taken for a change in position between any two identical Y positions on a different wave. So any of these positions would be calculated as the period. Specifically, we concluded that the system oscillated faster in the y direction, which made sense because the net force had a greater effect on the y component of motion. in comparison to the x component, which is only affected by the x component of the spring force. Like we said earlier, the net force varies directly with the change in speed with respect change in speed times the change in mass or the change in momentum. And so we can therefore conclude that a higher net force would equal a higher speed based off of this. And yeah, thank you.